All good. So yeah, good afternoon to those of you attending in person in Illinois. Well, good morning for me and anyone here within Australian time zone. Good evening if we have someone here from another side of the world. So my name is Eliza. I'm a PhD candidate from the University of Queensland, Australia. And today I'm going to present my work with the help of my advisory team, Jennifer, Paul, and Ilya, on our work on PFAS removal of activated carbon and ion exchange resin and beta-cyclodextrin polymer in various water matrices. So as this is the last session of the conference, I believe you all are aware, if not an expert, of what PFAS are and need no introduction. So as we all know, PFAS are persistent and stable chemicals. That is why they've been used in various industries. And for that same reason, PFAS has also been found everywhere, and PFAS pollution has been reported around the world, in the US, in Europe, and also here in Australia. The reported PFAS pollution sites are linked to PFAS hotspots or major point sources, such as industrial sites. But in my presentation today, I will just focus on fire training areas and wastewater treatment plants. So PFAS-containing firefighting foams can infiltrate groundwater sources or the surface waters. For instance, the nearby groundwater aquifer in a fire training facility here in Australia showed to have a PFAS concentration of more than 800 times higher than the PFAS detected in Australian drinking water. The blood serum of the people living in the area was also found to be 30 times higher than the general Australian population. So another major source of PFAS are wastewater treatment plants. Landfills serves as repositories for PFAS-contaminated products. PFAS may then be released to the groundwater or as form of leachate that would go to wastewater treatment plants. Several studies have showed the ineffectiveness of conventional wastewater treatment processes in removing these compounds. PFAS may be present in very low concentration in wastewater, like around nanograms per liter. However, these wastewater treatment plants receive up to 500 megaliters per day of wastewater and also discharges in high volume effluents. So because of this, various countermeasures have been put forward. Though health advisory values are currently non-enforceable, but due to public demand, strict implementation of these values may be applied in the near future, not only for drinking water, but who knows, also for the discharged effluent of wastewater treatment plants. So to achieve these guideline values, various remediation technologies are being explored. So since PFAS are present in low concentration in wastewater, it is important to remove them from the main wastewater stream to up-concentrate these chemicals prior to destruction. So there are various PFAS removal technologies, but among these, sorption is the most promising as it is efficient, simple, and cost-effective process. Thus, the objective of my work is to remove PFAS from water through sorption process. Here, I used industry best practice sorbents, activated carbon and an ion exchange resin, and an emerging sorbent beta-cyclodextrin polymer. I determined their PFAS removal efficiencies using environmentally relevant concentration, determined the effect of natural organic matter, and also determined their performance for environmental application using real wastewater and contaminated groundwater. So here is my experimental setup. I did batch absorption experiments using 100 ml milky water, then spiked it with 10 different PFAS, having an individual PFAS concentration of 50 micrograms per liter. I also used 50 milligram of sorbent in this solution. Sorption experiments were done for 24 hours. However, for the sorption kinetics, I collected samples at different time points. Then the aliquot was then centrifuged and the supernatant was subjected for PFAS analysis. So for the PFAS removal efficiency of the 3 sorbents, so here's the 24-hour sorption test of the three sorbents I've used, and in milky water spiked with 10 different PFAS. So as we can see from here that the 3 sorbents performed really well in removing the 10 PFAS that I've used, with the lowest removal of about 80%. We can see that among the 3, an ion exchange resin performed better, especially in removing short chain PFBA. So now looking into the sorption kinetics, we can see from here that activated carbon and beta-cyclodextrin polymer can remove more than 60% of PFAS just after 30 minutes. And sorption equilibrium was reached after 4 hours. However, for an ion exchange resin, only 20% of PFAS was removed after 30 minutes, and sorption equilibrium was reached after 8 hours. It is important to take note that the difference in the particle size of these three different these three different sorbents. So it can also be that other than their sorption mechanism, it may be that the particle size may also play an important role in their sorption kinetics. And because of that, it is an important point for a design consideration. So to determine the effect of NOM in PFAS removal, humic acid was used as a representative NOM, and then it was added at a concentration of 13 milligrams per liter. So the bar graph here shows the PFAS removal without NOM, and the colored symbols show the PFAS removal with NOM. So we can see from here for activated carbon, so the removal was almost similar with or without the presence of NOM. So it's not really the presence of humic acid didn't really inhibit the sorption process of activated carbon from this experiment. So for an ion exchange, however, we can see that removal of long chain PFAS for the 4-hour sorption test was inhibited, and then as the chain length of the PFAS increases, their removal kind of decreases. However, for the 24-hour sorption experiment, we can see that the presence of NOM did not really inhibit the PFAS removal on an ion exchange resin. So in the previous result that I've showed earlier, so I've mentioned that the sorption equilibrium of an ion exchange resin was reached after 8 hours. So it can be, or it is highly likely that the presence of humic acid inhibited the removal. So it is highly likely that the presence of NOM inhibited the sorption kinetics of an ion exchange resin for the 4-hour sorption experiment. And for the beta-cyclodextrin polymer, inhibition of PFBA removal can be seen, but removal of other PFAS didn't really show to be inhibited with the presence of humic acid. So next, one of the key questions that I want to know is that how effective are these sorbents in removing PFAS in real water matrices? So here I used domestic wastewater from a nearby wastewater treatment plant. The sample was taken after the primary treatment was named influent, and the effluent is the effluent discharged by the wastewater treatment plant received by the bay. So initial experiments showed that the wastewater did not contain any PFAS higher than 0.1 microgram per liter, which is the limit of detection of the equipment. Thus, we spiked the wastewater samples with 10 PFAS with concentration of 50 microgram per liter. So the bar graph shows the Milky Water experiment. The orange diamond symbols in here are the wastewater effluent, and the blue triangle in here are the PFAS removal in the wastewater influent. So as expected, we can see PFAS removal were lower in real wastewater matrices, especially for short chain PFAS. And this is true for the 3 different sorbents. Here we can see a chain length dependent sorption where the longer CF chain resulted to higher PFAS removal. And PFAS with sulfonic head groups, PFSAs, have higher PFAS removal in comparison to PFCAs of the same chain length. For example, looking into the PFBS, it has higher removal in comparison to PFBA. So, and here is, I want to show you the removal of the soluble COD in wastewater by the 3 different sorbents. From here, we can see that an ion exchange resin and activated carbon removes, probably also you all know, removes organic matter. However, beta-cyclodextrin polymer doesn't show to remove soluble COD. However, despite not removing the COD, it still shows to inhibit the presence of organic and inorganic contaminants in water, still shows to inhibit PFAS removal using cyclodextrin polymer. So lastly here, I want to show you the PFAS removal in contaminated groundwater. Preliminary experiments showed that the groundwater contained high concentration of PFAS, so we no longer needed to spike this water sample. So we were able to detect almost all the PFAS I used in the previous experiments, except for PFDA. Here, again, we can see a chain length dependent sorption. The higher the chain length, the higher the PFAS removal on all the sorbents. And we can see that an ion exchange resin performed better in removing short chain PFAS, while activated carbon performed better in removing longer chain PFAS. So to give you an overview, this figure here shows the 20 different PFAS detected in the contaminated groundwater and their initial concentration. So the highest PFAS concentration was PFHXS of about 291 microgram per liter, followed by PFOS and PFHXA. To wrap up, overall, this study shows that the sorbent's particle size may have an effect on desorption kinetics, and thus can be an important factor for design consideration. The presence of humic acid inhibited PFAS sorption on an ion exchange resin and cyclodextrin polymer. Activated carbon and the resin remove soluble COD, which strongly suggests that they are susceptible to biofouling in a wastewater context in comparison to the cyclodextrin polymer. Next is the presence of co-occurring organic and inorganic contaminants in real wastewater affected PFAS sorption, and not just wastewater, by the way, also in groundwater. And lastly, two consistent trends in PFAS removal was observed despite the difference in the background water used. So the longer the CF chain, the higher the PFAS removal. And with the same number of carbon, PFAS with the sulfonic head group, the PFSAs, were removed more in comparison to their carboxylic counterpart. So that's it. I would like to acknowledge the following organization who contributed to this work. Thank you.
We have time for one question if anybody has one. There's one in John.
Hello. So
Hello.
thank you. Number one, I wanted to ask you about the cost of the cyclodextrin as it compares to activated carbon or ion exchange resin.
Sorry, can you say it again?
The cost of the cyclodextrin sorbent, how does that compare to activated carbon or ion exchange resin?
Yeah, that's a good question. So I haven't really looked into their cost comparison yet, but I don't know if I'm allowed to disclose this material. I probably need some permission, but this yeah, sorry, I can't say much about it. Sorry.
Full of your closest friends.
Okay, that's okay. Number two, I also, it's great, you got a sorbent, right? But what do you do with the sorbent after it's spent?
Yeah, that's a good question. So the next one would be, of course, look into the different ways to regenerate it. As I think for now, the most common regeneration technique to recover the sorbent is the use of methanol. Yeah, but currently it's out of the scope of my topic. I haven't really looked deep or like really did regeneration experiments for the materials I've used. I focus more of like using them in a real wastewater context, kind of like that. So yeah.
Thank you. We're out of time, but I would encourage you, if you have additional questions for Eliza, to use the Whova app and send her message through that, and hopefully she can get back to you. Thank you very much.
Thank you.